So now let's put everything all together and pose to you a real problem. In this case, we'll talk about an RTG, or a radioisotope thermoelectric generator, which is supposed to produce a whole lot of power on a deep space mission. And let's say we want to know when this RTG is going to produce only 1 kilowatt of power, at which point the mission would be over. We'll start off by picking our isotope, and what's commonly used is plutonium-238, which has a decently long half-life, and we'll look that up in the table in just a sec. But let's say we start off with 10 kilograms of plutonium-238. And we want to know when will the power drop to 1 kilowatt. So let's deconstruct this problem a bit. If we have 10 kilograms of plutonium-238, we can calculate its total radioactivity. And if we know the Q value from each of those reactions, we can calculate its total power as it begins. And in order to get that, we just need to look up the half-life and the decay constant of plutonium-238. Since we're also going to need its molar mass at some point, let's write down its mass just to make sure. So first we'll grab two quantities, the mass of plutonium-238 and the Q value of alpha decay of plutonium-238. Nuclear is kind of known for its huge amount of subscripts, so this is perfectly normal. So let's head to the table, click somewhere up in the plutonium region. And there's plutonium right there. We'll look at plutonium-238. And we can see that it's got a mode of decay via alpha decay with a decay energy of 5.593 MeV. So let's write that down. You may be wondering at this point, why are we using the Q value? And why not the energy of the alpha particle? In module 1.1, we went through a lot of tedious calculations to get the energy of that alpha particle. So why are we just using Q now? Well, it turns out that the recoil or daughter nucleus of plutonium-238 decay also carries a fair bit of energy, and you actually need to account for that. So not only does the alpha carry off a fair bit of energy, in fact, we can use the table to look it up right now. If we go down to our alpha table, chances are we get about 5.499 MeV of energy, which is almost 5.593. And the rest of it, the remaining 50 to 100 keV, comes in the form of this uranium-234 nucleus, which it decays into. And we have to account for both of them because both of them contribute heat. Now the last thing to get is let's make sure to capture this mass of the plutonium atom. 238.0495534 AMU, which is pretty much the same units as grams per mole. Okay, so we've got all the things we need from our table of nuclides. So let's start calculating. First, we can answer the question, how much power did this RTG produce at time equals 0? So let's set up a little bit of unit analysis to get power, which is in watts. Let's call that W, which is the same as joules per second. So we need to somehow get from radioactivity, which we can calculate, to power, which, well, we'll get there. So anyway, we know that our power, which is in units of joules per second, is going to be related to our radioactivity, which is in becquerels, or decays per second, times the Q value. And this is given in MeVs per decay, which is to say that each singular decay gives us 5.593 MeV of energy times a conversion factor. 1.6 times 10 to the 13. And in this case, this is in joules per MeV. Let's do a little bit of unit analysis to make sure that we've got everything correct. We have a decay on the top and a decay on the bottom. We have an MeV on the top and an MeV on the bottom. And we're left with joules per second, just like joules per second. So we've got the right expression for power. We know the Q. We know this number. What's the activity? The radioactivity is defined as the decay constant times the number of atoms there. So at this point, we need to start figuring out what is the decay constant of plutonium-238, and for that we need its half-life. So if we scroll down on the table, you can see here that it's got a half-life of 87.7 years. And we need to convert that to seconds. So we actually multiply by our seconds to years conversion factor. And we end up getting 2.766 times 10 to the 9 seconds. And we also know that our decay constant is defined as the natural log of 2 over that half-life in seconds. And that comes out to 2.5091 times 10 to the minus 10 over seconds. Great. So we've got our decay constant right now. We can substitute that into here. Now we need to find out the number of plutonium atoms that we have. And for that, we know we have 10 kilograms of plutonium times 1,000 grams per kilogram. And we can divide by that molar mass of plutonium, 238.0495534 grams per mole. And since we need to know the number of atoms to get the number of disintegrations, we have to multiply by Avogadro's number, 6.023 times 10 to the 23rd atoms per mole. This is a good time to check our units, so let's do so. So we've got kilograms on the top, kilograms on the bottom. We've got a grams on the top and a grams on the bottom. This mole, which is on the bottom fraction on the bottom, is effectively on the top. We have a mole on the bottom, and we're left with a number of atoms. Great. Let's see, so this comes out to, let me grab my calculator here, 10 times 1,000 divided by the molar mass of plutonium times Avogadro's number. 2.529 times 10 to the 25 atoms. So finally, we can take that value right there, make that line a little bolder for you guys, and we can get our initial activity because we have the initial number of atoms. We just multiply those two together. We get initial activity of 6.3776 times 10 to the 15 becquerels. Great. So now we've got our A naught. So if we multiply these three numbers together, we get the power of the RTG when it was first turned on, when we had 10 kilograms of plutonium-238, and that comes to 5.707 kilowatts. We're almost there. Now we know the power of this RTG when it began, and we can use our radioactive decay equation to figure out at what time would it decrease to 1 kilowatt. So we're going to use our decay equation, A as a function of time equals A naught times e to the minus lambda t. We're going to modify it just a bit. What we note is here in this equation, power is directly proportional to activity via Q and this conversion factor. There should actually be a little negative sign in there. That's very important. There are not a lot of joules in an MeV. So we can actually replace activity with power on both sides of the equation. And we can say power at time t equals the power at time 0, e to the minus lambda t. And this makes things a lot easier because we have the power at time 0, and we want to know at what time this reaches 1 kilowatt. Not too hard to do. Because we know P, we know P0 is 5.707 kilowatts. We know our decay constant, which we already looked up to find as 2.5091 times 10 to the minus 10, 1 over seconds. All we're looking for is t. So let's start rearranging this equation a little bit. We can divide each side by p naught, noting that in this case the p naughts here cancel. And we end up with p over time over p naught equals e to the minus lambda t. We can take the natural log of both sides, because we're looking to isolate the stuff in the exponential right there. And we note in this case that the natural log of e to the something is just that something itself. So we can say that the log of p over t over p naught equals negative lambda t. We can divide each side by negative lambda, noting here that we've now got a minus lambda here and a minus lambda there. And we're left with a relatively simple equation. T equals negative 1 over lambda times the natural log of power at our given time over p naught. So we know lambda, we know p at t because we've set it at 1 kilowatt, and we know p naught. Finally, we can plug all these values in, and we first get a t in seconds of 6.942 times 10 to the 9th seconds. If we convert to years, we end up getting 220 years. That's a pretty decent deep space mission. So in this case, this space mission would last for about 220 years, which might be enough time to get awfully far out into the solar system and keep reporting a whole bunch of interesting astronomical data. Now I want to review just what we've done here, because we've pulled in a whole bunch of different pieces from this course together to do a fairly serious calculation. We started off with a pretty open-ended problem to say, when will the power drop to a kilowatt? We had to look up a bunch of values from the table. We had to make a conversion into lambda. We did a bunch of unit analysis to relate power to radioactivity via the Q number, which we looked up, and this conversion factor between joules and MeV. We noted that the radioactivity is the same as the decay constant times the number of atoms. We had to find the number of atoms, like in chemistry, using its molar mass, which we did. We found its initial activity. We changed our radiation equation to a power equation, noting that these two are directly proportional to each other. We rearranged a little bit of things, found an expression for t, and able to find a relatively reasonable answer.